Okay, hello, welcome. My name is Jimothy, and today I will be going through a video on some review of forces, as well as force system analysis and the assumptions that go along with solving these problems. Kind of a refresher of everything you need to do and learn before force system analysis. I can talk quite slow and I will be going over things quite slow. So if you want to speed me up, go ahead, put me on 2 times speed, make me sound like a chipmunk. But yeah, let's dive right into this. So going back to forces, right? We know from our equations that force equals mass times acceleration. So what does that mean? Well, if we have a box floating in space and this box has a mass, right? We can say, we can give it a mass of 10 kilograms. With the 10 kilograms, that means if we apply any force on that box, floating space, we push right here, that is going to cause this box to accelerate in this direction, right? And we have these arrows on top of the force and acceleration to show their vectors, meaning their direction matters, right? In this same example, if we have that same box over here and we have the force acting in this direction, we know it's going to accelerate in this direction. So if anything is accelerating, that means there's a force acting on it. And when there's a force acting on it, that sometimes means that it's accelerating. Now, what do I mean sometimes? So we also know another equation, sum of forces equals mass times acceleration. So we looked at one force, but again, if we have our nice box, this guy has a bit of a different hairdo, and we have force 1 acting on it, and let's say we also have a second force, force 2 acting on it. Well, that means that the mass times acceleration is going to be equal to the sum of these forces. So it's going to be something very big, bigger than the acceleration above, because that was one force. Where in this equation, if we expand it out, that little sum, we would get F1 plus F2, and that is going to equal mass times acceleration. So if we were just given these two forces and we knew the mass, that means we could solve for acceleration. So that seems pretty useful. If we know these forces, we can solve for acceleration. Same thing as if we knew one of the forces and acceleration and the mass, we could solve for force. And this example also works the other way, whereas if we have the same box, we bring it down here, but this time, this force, or we're going to say a new force, opposed on the opposite side, F2. And we can say those forces are equal. So this can equal 10 newtons, and this can equal 10 newtons. Well, in order to add them together, we need to decide on a direction because they're going opposite directions. So we intuitively know they can cancel out, but we should write our coordinate system here and say anything pointing in this direction, anything pointing in this direction with the arrow is a positive, meaning anything pointing to the other end here is going to be negative. So with that, we know this is going to be positive and this is going to be negative, right? And we'll add in the newtons right there. So again, if we do the F1 plus F2, we know we have our positive 10 newtons, and it's going to be plus, because again, this sum sign right up here, sigma sign, equal sum, which is add. So it's going to be plus negative 10 newtons, right? So you can't take away the plus sign and just do negative, but you're always adding them. It just happens that this is negative, equals mass times acceleration. But we see here that the 10 and the 10 are going to cancel out and give us 0. Mass times acceleration, which if we know that the mass equals 10 kilograms, and we also know that mass times acceleration equals 0, don't forget that hat, we know that acceleration must equal 0. Therefore, we can draw an important conclusion from this, which is equal and opposite forces cancel out, right? So this is a pretty fair summary of forces. There's just one more thing I want to go through, and we'll add a new page for that. And that is, lastly, with forces, is one of Newton's laws, which says every force has an equal and opposite force, right? So if we have this box, again, has a mass of 10 kilograms, and it is sitting on the ground. Looks like it's floating. We'll make that sit nice and right there. So it's sitting on the ground. This box is going to have a weight, and so this box is going to exert a force on the ground. We can maybe draw this force acting there. Actually, we'll do it better. We'll draw a nice force acting from gravity. Yeah, that's a bit small. I don't like that. There we go. Down. But this box is not sinking into the ground, and it's not moving. And we know if there's a force on an object, that it's going to move, right? Because we know if we have a force on the object, we have sum of forces, and that equals F1, and that right now is going to equal MA. We know it should be moving. That means that the ground is applying an equal and opposite force, right? So in this case, we know that we can say every force has an equal and opposite force. Whereas in our example above, you may be confused. Well, in our example above, we had that force moving it. Well, in our example, the box was floating in space, and we have a force acting here, but the box the outer edge of the box is going to be exerting a force, and that's an internal force, and that's going to make sure that this wall doesn't break. If that force wasn't there, right? Oh, that's a sad looking box. That's exactly what it would be, right? This force would be deforming the box, and therefore a lot of energy of this force would be used in breaking this box, and it would have a smaller acceleration. Whereas this has this nice, strong internal force going against it, which stops it from breaking the box. However, there's no force, there's no external force acting on the outside of the box, let's say here, to stop this force. So that may be a bit confusing. To summarize, this force is acting on the outside of the box. This box wall is pressing against to protect the box so it doesn't end up broken, right? However, if we put someone standing on the outside, that would be a third force that could then stop the box, just like in this example. But right now, if we did that here, we know this wall has a force and this wall to protect the side. And that assumption that there's that internal force protecting is assuming a rigid body, right? So you're assuming that whatever box or system you are looking at is rigid, and that when you apply a force, we assume all the energy of that force is used to move the object. I'll get back to the color coding. Acceleration is used to move the object, whereas in reality, we know that even on solid objects, some of that energy from that force is going to be used to deform it. So, assuming rigid body is going to more so say this is the case, not this. Another example of what would happen in reality is if you put a force at the bottom, right? And this object was, let's say, held on or glued to a wall up here. That's going to happen, right? It's going to bend. So that brings us to our assumptions. So we have one, this is in no particular order, rigid body, right? And we know it just means that our system is solid, and does not deform, right? And we have the second, and I will say the most important, hence why I started a new page, which is number 2. And that is assuming static equilibrium. And this one is particularly important, right? And this, if we go back to our first case, if we have a box mass, let's say we have a bunch of forces. Force 1, force 2, we can give a nice clean, let's say, move that one down a bit. And that's force 3. Static equilibrium assumes that assumes that the system or object you are looking at or analyzing is static. And that seems like I just basically extended static equilibrium into a sentence. That's exactly what I did. So what does this mean? Static means not moving. So it means that the sum of forces, which is equal to, we'll color code again, F2 plus F1 plus F3 equals 0. And why is that important? Well, because if sum of forces equals 0, we also know that means mass times acceleration equals 0. Therefore, if it's not accelerating, in this case, we're assuming it's not moving. So this, in these cases, in force system analysis, we're assuming it's not accelerating, so it's kind of static in place. Not moving. Right? So the forces are not causing it to move. Could have velocity, but we will not get into that. And so one thing I want to talk about is, I've used this word a couple of times, and I think, in my opinion, it causes the most amount of pain and confusion in doing force system analysis. And that's the S in FSA, system, right? The system is solid, we're assuming. We're assuming the system is in static equilibrium. Well, what is the system? So let's go ahead and define system. I apologize for my writing, but I am speaking out my sentences. So therefore, that should counteract the pain of trying to read it. So the system can be defined in many ways. I like to define it as the object that has forces. We'll move this down. That has forces and moments acting on it. That seems pretty simple, and it kind of is, because I feel like a technical definition can get confusing, and the best way to learn about what a system is and how to define a system is to do examples. So it has the object that has forces and moments acting on it. So in this case here, we'll bring this down here. The system is the perimeter of this box, because the forces are acting on it. So I like to see the on. The on is very important, because that is, in my mind, external, right? Forces acting, if I were to think of it, forces acting, make that an A, on Jimothy means something's acting on Jimothy, whereas if you go forces acting in Jimothy, well, it seems internal, and this is external. So it is basically setting up the thing, setting up the object so you can assess and analyze the external forces. So the object or objects, so it's that object or objects, so you can analyze the forces acting on it and negate the forces acting within it. And that last part, negate the forces acting within it. That is only because, we'll slide this up so I can write that because that's important. This part is only because it is rigid body plus static equilibrium. So the system is object that has forces and moments acting on it. So basically, the thing that external forces are acting on. And what that helps us do, it helps us analyze the forces acting on it. And we can negate those internal ones, right? And those internal ones, again, like if we were to get, are going to be just blocking out these ones so that the cube isn't crushed into some, I don't know, sad cube, right? Because like this does not look like a happy cube. Very sad. Now to hop into an example I've set up, we are looking at Jimothy, me in the gym doing tricep extensions. And in this case, doing 50 kilograms. And to set up a system, we first have to know what we want to solve for. And so before we even start the question or look at the question, we're going to assume static equilibrium as well as rigid body. We can also go ahead and state a coordinate system, but we're not actually solving here, we're just setting up the system. But in order to set up that system, we need to know what we're solving for. So if in this example, we want to find mass of Jimothy. We'll just call it J-man to save room. So we have our definition of just the system is the object we're looking at, and we're looking at the external forces being applied to it. So I like to think of when you define a system, you freeze it. Why do you freeze it? It is not moving and it is rigid. So it acts the same way as almost an ice cube or a frozen thing would. So that helps me get through and kind of visualize these two assumptions, and just for solving the problem, just thinking about it. So for example, he's doing this weight, he's lifting it. If I were to choose everything as the system, well, I would freeze everything but the ground. I would freeze Jimothy and this whole weight rack thing, right? So this is my system, this big block of ice that just so happens to be the shape of Jimothy and this system. And we know this system is in static equilibrium, and we know it's not moving. We also know it has a weight. Now the weight of this system is going to be Jimothy's weight plus this whole weight of this rack and apparatus. So we know it's going to have a force here. We'll draw that in green. And we know, though, static equilibrium, sum of forces equals 0, which means mass times acceleration equals 0. Therefore, we know acceleration equals 0. It is not moving. So Jimothy's not sinking into the ground. So we know there has to be some ground reaction force. And in this case, it's shaped odd. And so you have 3 because it's a big block of ice with 3 things to the ground. Well, that does not help us find the mass of J-Man Jimothy, right? So that's not a good system to choose. What do we want? We want the mass of Jimothy. So we're going to do our system as Jimothy. We'll grab him right here and the ground. Right? And now we can have Jimothy as our system. Again, a frozen block of ice. And what's an external force acting? Well, now this pulley. Before, when we had the system as all of this, right, we do have a force here acting this way on the pulley. This is going down, so then has a force on both sides. So like these forces are internal, right? If this isn't moving, there are forces counteracting it. So that was a bad example. We'll go more into detail into the one we're doing, right? We have this force of the pulley now because it's external, plus we have the weight. We can call this just W, the force of the weight of Jimothy, or mass, but weight, we'll use weight. And then we know that again, we have some ground reaction force. We can call ground reaction force. Now, does this allow us to see the mass? Well, weight first, and then we can solve for mass of Jimothy. Yes, right? We have what we need to solve the equation. And now I'm going to talk about what I said on this previous slide, where I was saying that to negate those internal forces. What I'm talking about. Since it's static equilibrium, we're assuming a rigid body. We're assuming this whole thing is rigid. Hence why I think of it as you're freezing an ice cube, right? So if I bring this out, clean it up a bit, and we make it bigger so we can see everything, right? We know those 3 forces, we'll add them. Force, force, and again, we'll just draw the ice cube, right? And then there's that. We'll draw the internal force on the outside just so I can use the inside in a sec. We know there's these 3 forces. They're all external because gravity, this weight one, the weight you might think, oh, that acting here, yeah. But gravity is an external force, which is causing that force, right? So gravity is happening on the whole system, so it's an external force. You just draw it in the middle. But inside here, if we look at that knee joint, we know there's this force shooting up. Now, if we looked at just the knee, if we just try to grab the knee, we'll draw it blue. This is just the whole bottom part of the leg, right? That's lower leg. If we were to grab this bottom force here is not shooting this leg up. The leg is staying attached to Jimothy, right? It's not shooting off. Therefore, there's no acceleration. So just looking at this leg, we have our force on it. If this was our system, we'd know there has to be some force at the knee. We'll do a different color there. Has to be some force at the knee so that when we add them up, it equals 0. Because without that force at the knee, we have F equals 0, which is not the case. So we know that since that leg's not flying out, that there has to be this force here, right? And if we were to choose the other part of the leg, the quad, this is a quad. That's a bad quad. There's a belt. That's their leg. They're wearing shorts. Okay. Right? If we were to use this part, right? We know that if there's a force acting down here, right? This guy, all the weight of the body's pushing down, not accelerating down, that there has to be some force again, keeping this together, right? And so when these are put together, these two gray forces cancel out. Now, that was just a visualization. A more technical way you can think of it is each segment, the calf area here, and the quads here, calf here, they're not moving away from each other. Therefore, the forces between them must be equal and opposite and cancel out. So therefore, that's the same for everything within this ice cube, right? Shoulder joint has forces, but they're equal and opposite, right? Like bicep is flexing this way, tricep here, like the elbow joint is not moving off of the body. Therefore, since the body is one solid piece that is not moving, right? That means, right, A is 0, which means sum of forces equals 0. So since the body's one solid piece that is not moving, we know that the internal forces cancel out. Therefore, we can focus and analyze only the external forces. Right? And does that make sense? Like in this case, we wanted the weight, and so we defined the system as just Jimothy, and we were able to find that weight, which you're right, should be right in the middle here. And we would be able to solve for if we were given more numbers and all the information. So that's for solving the mass. Here, if we want to do something different, solve for tricep force. Now I'm going to give you the steps now. We've done one example, and then the steps to defining the system is to define a system. This seems backward, but I wanted to illustrate it with one example and then define it and then show through another how to use these steps. To define the system, you first find/identify the force, or I guess you could do moment. We'll just stick with force right now. We haven't talked about that. Force that you want to solve for. Step 2, define the system in a way that makes that force, makes that desired or unknown force, we'll call it the desired force, an external force, right? Inside here, this first example, right over here, that mass, lots of things have mass. So that's inside the system. And all these masses are counteracted by, right, gravity. Or I guess these are technically gravity, like I said, is external, but there's multiple of them. So you can't differentiate them. That's a better word. So we want to define the system in a way that makes that desired force an external force. So we are going to practice with that tricep one. So to first, we need to identify the force you want to solve for. And so if we want to solve for tricep force, we need to take a bit more another anatomy lesson. That's why this is biomechanics. It's not just rely on physics, you need to know your anatomy. So, looking, this is the hand, right? Then you have your radius and ulna. You know that the triceps all insert onto the ulna, right? Then you have your big muscle. One inserts here, and then the rest on the scapula, right? In this case, I'm pulling my hands down, right? And my triceps going to be contracting, producing a force this way, right? And there's a force pulling up. So, in this example, if I were to make the entire shoulder the entire forearm the system, would that be helpful? I'll redraw it because you're right, the tricep is part of it. Would this be helpful? You may think, oh, well, they have one force. But if you think about it, the tricep is in the middle, and technically it inserts somewhat on the humerus, somewhat on the scapula. So there's an internal force this way, right? Let's clear up that blue ice cube, right? So this technically encapsulates the whole tricep, right? And when you encapsulate the whole tricep, both sides, they both have force pulling on each other, pulling on each thing, and that's what shortens it, right? You can think of it, you have it here, and it's on like a string, and this middle part shrinks, right? That's going to pull the string on this side and pull the string on this side. So this doesn't really help us because if we do sum of forces, and we call this force 1, 2, 3, it's going to be force 1 plus force 2 plus force 3, and we know these are going to cancel out because they're from the same muscle and they're in opposite directions. So what we want to do is we want to make them external. So what I'm going to do is I'm going to define the system. I'm going to define the system as just the forearm. Right? When I do that, I define it just as the forearm. Now we know there's only one side of that force. There's only one side of that force pulling. And now we would be able to solve for this force. We would further do our free body diagram, and we know that the elbow does sit here, so we would know that there is some Fy and some Fx force at the elbow, but we in fact have our wanted force, which we can then solve for. Before, we didn't. And this goes for any muscle. Like if we were to do the quad, I'll draw a quick quad. That's the heel, calf, quad. There, sitting up. There, having a nice, good quad extension. Right? If you have the muscle here, if the entire thing is in your system, if the entire, any muscle is in your system, the forces cancel out. So if you want to look at any muscle, you kind of have to cut it off at one side. And then you know that that gives you a force here. Because if you look at the muscle, if you look at a muscle, this is a great muscle. I know, I'm an artist. If you look at a muscle, it pulls as this middle part gets shorter, it pulls on both sides, right? As each side pulls, and that causes force, right? As each, the blue is just it moving inward, it's pulling on either side at the same time. So if you have your system as the entire thing, it cancels out, right? But if you have your system on one side, you can then look at that force. This will be helpful in the stress strain calculations and stuff everyone will do in later courses or the current course you're in. I hope this helps. Don't be freaked out if you're like, well, how do I apply this to a problem? You will get lots of practice. But if you have any questions, concerns, you want me to make a video on a certain topic, reviewing maybe moments, that'll be for anything you want. Let me know. Comment any questions, message me, and thank you for watching. Hopefully you watch this on 2x speed. If not, wow, that must have been brutal. So thank you. Have a good one.